You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Megan Donahue. Dr. Megan Donahue is a University Distinguished Professor of Physics and Astronomy at Michigan State University, whose research focuses on galaxy clusters and the distribution of baryonic matter in the universe. She studies cluster evolution to understand cosmic structure and matter density. A Fellow of the American Physical Society, she was recognized for her contributions to cosmological observations. She served as president of the American Astronomical Society from 2017 to 2020.
Dr. Megan Donahue, welcome to the program.
Thank you.
Now, Doctor, your expertise is in deep astronomy, really, but we have a potential problem. And that is a completed telescope that is almost ready for launch that is in danger of being canceled. And I can't think of anything more wasteful than that when the telescope is about ready to go. But on top of that, it was originally designed to repurpose a mirror that was from a spy satellite, which was government waste. So it was trying to fix government waste, and now we're going to waste that. How did the Nancy Grace Roman telescope idea come about? And I know it traces back to a decadal survey. Tell us about that.
Well, you're asking one of the people who was on the committee that looked at those telescope projects in 2008, 2009, when we started to review the white papers for the 2010 survey. And we were getting a number of proposals that used the same sort of telescope architecture, about the same size mirror, looking in the near infrared, so it would be optimized for the standard part of the electromagnetic spectrum, but doing slightly different science. And so that committee decided, rightly or wrongly, to sort of merge all those projects together into one telescope with a few different main scientific projects to be accomplished by that telescope. And so that was the beginning of the Nancy Roman telescope. It was originally called WFIRST.
I remember when it was called WFIRST. And in fact, this telescope is noteworthy because its objective main mirror is the size of the Hubble Space Telescope. However, it is more wider field. Explain how that works.
You can make a telescope that can look in a very narrow field, or you can make a telescope to have a wide field. It's sort of like having a telephoto lens for your camera versus a regular lens. So the geometry of the optical system sets your field of view. So this is sort of a wide field of view. So it's a different geometry. It'll look different from the Hubble Space Telescope in terms of its length compared to its diameter. So it's optimized for very, very wide field, whereas the Hubble Space Telescope has a very, very tiny field of view.
Now, what is the advantage of that in astronomical observation?
Well, you get more of the sky at one go. So the coverage of the Hubble Space Telescope is sort of, someone once described to me, if you take the eye of the Roosevelt on the dime and hold it at arm's length, that's about how much sky the Hubble Space Telescope can cover in just one shot. And the Roman telescope will cover something bigger than the full moon. So a couple degrees across, so about 4 full moons across.
That's gonna make some interesting deep field images, right?
Absolutely. So the Hubble deep fields that you see in that, little eye of the Roosevelt, have maybe a few thousand galaxies. So you multiply that by 100 or 200, and that's what you'll get in one go with Roman.
Now, how does that field of view stack up to James Webb? In other words, what is the Webb telescope's field of view in comparison to these?
James Webb's telescope is, in some sense, even smaller than Hubble's. It's a much bigger mirror, so it can peer farther into the past. And also, it has redder or longer wavelength coverage, so it can see light that's been more redshifted, but it's a smaller field of view. It's a bigger camera, though. It's a bigger mirror, so it's more sensitive. Roman will have the same sensitivity as Hubble. It'll have the same sort of acuity as Hubble, the same sort of precise vision that Hubble has, but over a much wider field of view. So we'll get a lot of stuff simultaneously. You never could cover as much sky as Roman will be able to cover in its lifespan, even if Hubble lasted another 20, 30 years, which it won't, unfortunately.
No, unfortunately not, but we certainly got our money's worth with that one.
We did. We do.
We
And
did.
we still are.
And still are. And in fact, it itself, who could forget? It was a mess up. The mirror was ground wrong. I believe it was PerkinElmer that did that. And it was ground incorrectly, and we had to give it eyeglasses and basically correct its vision. But this is not the case with the Roman telescope. This one was born from, it was designed to be a spy satellite,
Right.
a clandestine spy satellite. And I can certainly see why a wide field of view would be useful there if you're looking down towards the Earth. But they didn't use it there. They had a whole array of these types of spy satellites, and they ended up with 2 mirrors left over. And one of them is, I believe it was the NRO or whoever donated them to NASA, thinking, well, we can repurpose these, maybe make a telescope, just don't point it towards the Earth. So there were 2 mirrors, and one of them is the Roman telescope. There is another mirror in storage. Is there any plans for that one?
I don't believe so. I mean, especially not for launching, because even though they had the telescope's mirror in place and they had some of the assembly, they still had to design the camera and build the spacecraft and so forth. So having the mirror didn't make Roman that much cheaper. So it would still cost about the same as it cost to make Roman, to make another space telescope from that mirror. I think I heard that people had considered putting it into a ground-based telescope, possibly. But as far as I know, there's no specific plans for that.
That'd be interesting to do a ground-based telescope with it.
Yeah, I mean, a 2.4 meter on the ground is it's not too shabby.
Now, telescope technology, when we launched Hubble, and Roman for that matter, that mirror is actually decades old. That's in Roman. It's repurposed from, these spy satellites from, I believe, the 1980s. And the thing is, though, is that these look very different. These are those huge single pieces of glass mirrors, and they're heavy. They're, even though they have air spaces and all that stuff, they're heavy, and they're not what we used with JWST, which has segmented mirrors.
That's right.
Would we build a telescope from scratch like this now? Say we wanted to build a wide field telescope, say the European Space Agency or somebody wants one, and they have to build it from the ground up. Would they still do it this way with a single piece of glass, or would they go with a segmented mirror for a space telescope?
That's an interesting question. It probably depends on the size. If you're building a 1 or 2 meter class telescope, you still might use a single piece of glass because that simplifies other aspects of the engineering. One of the challenges for James Webb was the tuning up the mirrors, testing the mirrors. Everything had to work just so. All the actuators that you had presented a fairly high engineering challenge. So if you could, you're always in trade space. You're trading off weight versus complexity sometimes. And there's sometimes you just go, well, we can launch it. So we'll take the weight.
Actually, I can certainly see that, because remember, there was something like 240 failure points for James Webb, and it made it past all of them, which I guess is by virtue of having had plenty of time to test it because of the delays. But
doesn't mean it wasn't terrifying.
Yeah, well, that was terrifying, because I'm thinking, man, if this thing doesn't work, but it went off so perfectly, and it has performed actually better than perfectly, because perfect would say it was doing 100% of what it was designed to do, but it's doing better than that.
That's right.
We got a better telescope than we bargained for.
In margin, and some of that margin came through in the positive. So
yes, indeed. Now, and I have no doubt that would happen with Roman as well. If the funding continues, when will Roman launch a first light and start returning science?
Well, if everything goes as planned, the program tells me that they could launch Roman as early as October 2026. Their deal with Congress that was sort of renegotiated after COVID moved that latest launch date to May 2027. But based on testing and things like the shake test and other integration tests, they've had a lot of good outcomes and things they can easily fix. And so they have a lot of margin, as they say, in their schedule. And so they're pointed at an October 2026 date, and they're still holding to that. They could slip it as late as May 2027, but that's not looking necessary given the testing and things so forth.
Now, you mentioned a shake test. What is that? Is that when you have to actually make sure that this telescope can survive being stuck on top of a very shaky rocket and launched with
Yes.
great vigor into space?
Yes, that it can survive the rigors of launch. And because once it's in space, it's relatively calm and serene. I mean, there can be micrometeorites or something like that, but the scariest point for a telescope is launch, where things can get shaken. You don't want like something slipping over the cover and then latching it down forever or something like that. So they really put it through its paces and give something far more rigorous than what they think would be experienced during launch, just in case. So by the time it gets to that launch pad, they know that all the pieces that might come off are already off.
This might be somewhat nuts and bolts, but I'm fascinated with telescopes because I've been an amateur astronomer since I was a teenager, actually a little bit before then, which was the 1980s. But the thing is I know from my telescopes, my trusty Celestron and my Dobsonian and all of those, that if you go for a cross-country move with one of those things in the back of a truck, that mirror goes out of alignment when you have to sit there and realign very carefully. And do you have to do that with a space telescope? In other words, do you have actuators and everything to be able to reposition that mirror?
Yeah, you have some tolerance to move the alignment during test and then during any kind of shaking. And then you have the capacity to bring things back into alignment and focus. So first light is always kind of another scary moment. But once you get light into the detector, you usually have the capacity to drive things around and bring things back into both, as you know, from an amateur telescope, you have to get everything into parallel and then bring it into focus.
Now the planned science with the Nancy Grace Roman telescope is varied, extremely varied, just like JWST. You can do a lot with it. In this case, though, there is a sort of interesting aspect, and that is exoplanet research, in that Roman is built in part for that. Can you tell us about that aspect of what the operations of this telescope will look like?
Well, there's two exoplanet programs. One is a program to look at the architecture of external solar systems through microlensing, and also the more traditional way of monitoring stars and looking for the transits. So that's one method that they're going to use to study. They'll have thousands and thousands of stars in a given field of view. They can monitor it for microlensing events where a dark object might pass in front of a star and then cause it, through its lensing of its gravity, to spike briefly. That's interesting because, it seems so hard, but you can look for very dark, very small objects in the sense of, this technique's been used to look for possible candidates for dark matter, for example. The other technique is to be able to block out the light of the central star and then look around the blocked out part of your field of view for light reflected by a planet. And that's not a core science case for Roman because it's in the very experimental phase. But they argued it was important enough that they were able to get it on as a feature of the telescope, this interferon.
Now, these microlensing events, there are multiple aspects to that, really, because gravitational lensing is really interesting. That was on a large scale with a galaxy cluster or something like that. You can see it.
You can just see it.
You can see it, the Einstein rings and things like that, which means that you can actually measure differences in timing when the light gets to you, and you can do all kinds of cool things with that.
Yes.
And it was my favorite part of it is it was a prediction of general relativity,
right.
But and it turned out to be there, and we use it now. But the thing is, these microlensing events, what's doing it? What are the dark objects passing by? Is it just dimmer stars like a red dwarf or something, or is it?
Right.
Could it even be rogue planets?
Yes, anything that is, it would have to be bigger than a moon. But planets and stars both have mass, and so it can bend light. Matter bends light. That's what general relativity tells us. So if something drifted in alignment between us and a background star, it can temporarily lens the light from that background star, making it magnify into visibility and then back out. And by studying these events, They're actually just one-off events. We'll never be able to go back to a microlensing event and see it again. So that's why you need to watch like 10 million stars and monitor them all. And you'll get a certain fraction of those stars will experience microlensing events, which you can distinguish from other kinds of variability, because what microlensing does is it takes all of the light, no matter what wavelength it is, magnifies it up, and then it goes down together. And any other kind of variability like flares and stuff always have different features of the spectrum that go up and down at different times. So they're able to discern those events from other kinds of variability. And the pattern of light can they've been able to show, yes, there was a planet, especially the planets that would be harder for us to detect any other way. They call the cold planets. The planets that are farther away from their host stars. We'll be able to count how many systems have planets beyond 5 astronomical units, where you can't wait for transits, to happen every 20 years, for example. But we'll be able to count how many how many star systems have certain kinds of architectures. We'll be able to answer the question, for example, how many stars out there have cold Jupiters and cold Saturns like our solar system? That's something that's much harder to answer with just pure transit monitoring, like what TESS is doing.
So when you're dealing with something that's effectively a transient, a gravitational microlensing event, this almost reminds me more of like the Kepler Space Telescope, where you just stare at one spot and you do it for a very long period. What is the time profile of the observations for this with Roman? Are we going to just be staring at the same spot for a while to hopefully catch it?
Yep. For that particular science case, yes. They'll be staring at parts of the bulge of our own galaxy. So they'll be looking at stars in our own galaxy. So at the same time, they'll be able to do transit photometry as well. So they'll be able to also do the same kinds of things that Kepler was able to do, except they'll be sensitive to even smaller planets because the photometry will be more precise. The point source of the background star will be better. So it's a bigger telescope, and it'll be able to go both deeper, see fainter stars. So they'll be able to do the transits as well as look for microlensing.
So can we kill 2 birds or more with a single stone here in this specific case where you're looking at something and you've got one astronomer that says, I'm interested in this star, HD, whatever catalog phone number it has. But another astronomer said, you made that observation, but you got an object I'm interested in there, in that wide field. Give me the data so I can take a look at that. Is that where this is going to go?
Absolutely. All the data that Roman takes will be instantly public. So it will be on the cloud and available for everyone. They are conducting a few community surveys with planned pointings and so forth, so people can make plans about, they're going to see my favorite cluster of galaxies as well as, all these other galaxies in their deep fields. So yes, in a field that's 2 degrees across, that has the resolution of Hubble, there'll be a lot of objects that astronomers are interested in that same picture. So people will tend to collect data in a generalizably usable way, and it will be shared through cloud technology. And people will be able to analyze it, probably not by downloading it like you can do with a Hubble image, but by analyzing it in sort of virtual sandboxes through cloud technology.
Sounds like efficiency to me. Sounds like a very productive telescope because of the amount, much more so than anything we have, I think.
Well, yes, I agree, because every deep image will have multiple science cases. So if you're looking at an extragalactic field, you can imagine a project that went and looked for Einstein rings around individual galaxies. And you would get that along with all the other gravitational lensing projects that you can imagine doing. Those are hard. So the observations that are designed to look for that weak statistical gravitational lensing signature of all the dark matter between us and background galaxies, that same data can be used to study the galaxies themselves at exquisite detail. So there's just all kinds of science cases that will use the survey data. And they also have a fraction of the time, I believe it's like a third or a half, that will also be open for competitive proposals for projects like take a survey of the local group galaxies So Andromeda, our sister galaxy, has an image that was collected by Hubble over a couple hundred pointings to image all of Andromeda. Roman would be able to cover Andromeda in two shots. And so a lot of these local galaxies where we can see the individual stars, and we'll be able to map them out in one or two goes. And that will be, I can imagine that would be an obvious general observer project that someone will propose. And the science that you can do with that, you can get the star formation history of local group galaxies. At the same time, you can look at all the background galaxies in that same field. So it's going to be fun.
Now, with JWST, obviously, the early universe is its main function, looking at the very earliest galaxies. But being smaller, this is less of a thing for the Roman telescope. Well, what can it do in that as far as probing cosmology and the early universe? What can we do there?
Well, one of its primary objectives is to measure how dark energy has changed over cosmic time. And that requires looking at distant galaxies, but you don't have to look back to the James Webb Redshift 11 galaxies to see how dark energy has changed, because dark energy, as far as we can tell, really started to kick in and accelerate the expansion of the universe relatively recently. So if we're looking at how dark energy has changed over time, we don't have to push back to farthest, most distant galaxies we can see. We just have to push back to galaxies where we can track their, well, a lot of features, their supernova rates and their weak lensing signatures, and look at how dark energy has affected the expansion since that time. So one of the interesting things that came out recently was that the standard model for dark energy is a dark energy that behaves like a vacuum energy. And a vacuum energy has a very specific behavior pattern. It's constant. It doesn't change with time. As the universe expands, the amount of vacuum gets bigger, so the influence of dark energy gets bigger. But if it's not based on the vacuum energy, then it might have different properties. It might have been bigger in the past. It might have been smaller in the past. And so there's a hint that it has been increasing with time. There is a big survey from the 4-meter telescope in Arizona. I'm blanking on its name now. It's based on the Sloan Sky Survey, and it's spectra. And they count millions of spectra of galaxies to measure their positions in both the plane of the sky, but also in redshift space. And they could use those positions to track a feature that expands with the expansion of the universe. And so there they can track how the universe has expanded with time by looking for this feature called baryonic acoustic oscillations. And I'm probably getting a little too technical here, but the upshot is that particular experiment had a very specific expectation that was set down by the assumption that dark energy behaves like a vacuum energy density. And the actual measurement showed a sort of 2 or 3 sigma-ish deviation from that expectation. And what that means is there's a possibility that dark energy doesn't behave like, I don't want to call it a boring vacuum energy, because even that was completely unexpected. But there's this possibility that there might be some change of dark energy with time that is above and beyond what you'd expect from a vacuum energy, cosmological constant kind of dark energy. And that's very exciting, because maybe that's part of the explanation for some of the Hubble constant differences that have been measured by Adam Rees using supernova to get in distant galaxies, compared to the Hubble constant that's inferred from the cosmic microwave background experiments that sort of measure a version of this baryonic acoustic oscillation, but at a redshift of 1,000.
And it is rather spooky, because changing dark energy ultimately dictates the end of the universe, what will happen. And if we don't even know what dark energy is yet,
no.
We have no idea. All we know is that you need some kind of energy to be doing what we're seeing. And now it's changing. It's changed since the Big Bang.
Yes.
Well, what changes in the future? And these all dictate what happens to the universe, frankly.
Yes. I tell my students, we know for sure it's not matter. So that leaves the other thing. It has to be energy. And the name dark energy, I think gave it that little, ring of I don't know, cuteness. I don't know. But it paired well with the whole dark matter idea, where we also don't know what makes up dark matter. Pretty sure it's matter. We're pretty sure of some of the properties of that matter, but we don't know. We don't even know whether it's like one kind of matter or multiple kinds of matter. I hate to say, it could be more than one kind of dark energy too. I don't even want to go there, but yeah, we know very little about dark energy except for its energy density, and we know a bit about how it's changed with time. But we could that second thing is something that we'll be able to tie down very, very rigorously with the Roman Space Telescope.
That's one of the interesting things about that, is that with dark matter, you do have a piece of evidence. Excess gravity. We see too much gravity for the mass that we know is there. Therefore, there must be more mass somehow. And that mass may be non-interactive, but that isn't really all that surprising because the neutrino is that way. It doesn't like to interact. So it kind of is a particle of dark matter. And so it's not a far stretch to say, well, maybe there's another kind of particle. And the same with dark energy. We see the effect, but we don't know what the source is. But there, like the neutrino, we have something weird, and I believe it's called the Casimir effect, where you have a kind of energy there that's getting sort of in that territory. Would you agree with that statement?
Yeah, the vacuum energy density has been tested through this Casimir effect in laboratories. And the thing about it, right, is that dark energy is of great interest to quantum physicists, because they have this issue when they attempted to estimate the magnitude of the dark energy 0 point. They got a number that was 10 to the 120 times bigger than we've measured, right? So in the units we've measured it, dark energy has a value of about 0.7. In the late 20th century, people knew that if there was a dark energy or a cosmological constant in those same units, it had to be less than something about like 2. I mean, that's pretty conservative. And so it was fairly common in the 20th century just to set it to 0. And when quantum physicists tried to calculate what that number is, they got a number that in those same units came out to 10 to the 120. So like 1 with 120 zeros after it. They said, well, that's obviously wrong. That would be something we would certainly be able to measure. And maybe we wouldn't even exist in a universe that had dark energy of that magnitude. Probably not. So they decided maybe it was exactly 0. So there was a sort of a tendency, at least among astronomers, cosmologists, and quantum physicists, to say, well, there's this cosmological constant and it probably gets balanced out somehow, right? And it wasn't until cosmologists studying type 1a supernova and in distant galaxies, and the expected expansion rate was turning out to be accelerating. So that was sort of the irrefutable evidence at that time that was just hard to get around. It was gravity would inevitably decelerate the expansion of the universe, and yet they were seeing an acceleration. And then with that information, they could put a number on the energy density of dark energy, and that number comes out to a normalized value, a unitless value of 0.7-ish.
Now, astrobiology with the Roman telescope, what can we do there? Because I know that that's a hot and very contentious field right now because of certain gases being detected by Webb, but which we don't know, it's all up in the air. But what can be done there as far as looking for biosignature gases and things like that with the Roman telescope?
Well, to be frank, not as much, because James Webb has the spectroscopy. So James Webb has the near-infrared and mid-infrared spectrographs that can see the signature of absorption features due to things like water or carbon dioxide or methane and so forth in the spectra of planets as they pass in front of their host stars. Roman doesn't have that kind of spectroscopy capability, so it will not be a life finder. at least in that sense.
What of, now you mentioned type 1a supernovae, what of that? Because that's useful in a field of view when you're looking for something that you don't know is going to happen in a distant galaxy, and there it cooks off, and when you got a wide field of view, you have a better chance of catching it.
Absolutely.
Is that I figured that would be on the agenda.
Yes.
Because you could do so much with different measurements to infer things regarding those. So it's going to be a supernova hunter.
It's exactly. So what they'll do is the same fields where they'll be studying the signatures of weak lensing coming from dark matter. They'll be going back to that same field and building a deeper and deeper field for the weak lensing experiment. But the multiple visits for the field means they'll have a time-lapse photograph of that same field. So using specially chosen cadences that they've developed over the years with ground-based searches for supernova, they'll be using a similar cadence to both build up a fantastic picture for the other cosmology work, but that same set of data can be used to get a time lapse of all the galaxies in that same field of view, which is going to be hundreds of thousands, and they'll be able to find the supernova in those fields of view. And they'll also have estimates for their redshifts and so forth straight away.
Now, there is one special interest I have in astronomy, just because I'm fascinated with it, is the idea of a supernova that can not happen. In other words, it just, instead of the supernova occurring, it collapses into a black hole without any explosion or intermediary change. It just, boom, the supernova essentially falls in on itself for a certain massive star. Is there anything there that we could look for to kind of confirm that? I know that's a hypothetical, but will we see stars disappear? Certain masses just poof, gone, and you still see the gravity, but you don't see the star.
Well, the idea would be the star before it goes, right, would be a very massive star. So it would be bright. And you can see with the acuity of a Roman space telescope, you can see individual stars in other galaxies. And so if you go and you visit, say, a local group galaxy or a galaxy that's forming a lot of stars, today you keep going back to that galaxy, you might see a bright star disappear, right? But it wouldn't have the unmissable supernova signature afterwards, right? So if you're using that supernova discovery cadence, you'd also be able to track the bright stars and see if one goes away. Now it would probably be a lucky observation, because even in our own galaxy, supernova are pretty rare. So monitoring even billions of stars in another galaxy, you'd still have to kind of get lucky to catch one that just goes wink.
Yeah, but with instruments, not just with Roman, but things like the Vera Rubin telescope, with survey telescopes like that, that's going to be interesting, because not so much in the case of the supernova that doesn't happen, but in anything transient, that we can actually see at a cadence much, much faster and at higher resolution, if you will, than ever before, where it was just like with Hubble, you're just looking one tiny little spot moving around, very targeted, you know what you're going for. But what are the stuff that you don't know it's going to happen, and that's why wide field is important.
That's right.
Now, in your work as an astronomer, will you be trying to book time on the Roman telescope, and what would you do?
Well, my specialty is studying clusters of galaxies, and clusters of galaxies are they're the most massive structures in the universe. And so their internal structure, their numbers as a function of their mass, and how they change over cosmic time all depend on cosmology, and in particular depend on the amount of dark matter that's present in the universe. So I'm very interested in these clusters of galaxies. So I'm sure that me or somebody as interested in clusters as me will be using Roman to study clusters of galaxies, because they're rare enough that you can't just get them in a random, even a 2-degree field of view doesn't have a whole lot of clusters of galaxies. It might have one of these big, massive galaxy clusters in it. So if you want to study a sample of those, you would use a pointed survey, but it would be gorgeous. I mean, Hubble Space Telescope and James Webb have both used massive telescopes to peer into the early universe because they're great cosmic lenses. And Roman will be able to map their dark matter structure way, way out, well beyond the range that James Webb or Hubble can map them. And so we're interested in how these things connect to each other. The web of dark matter on the sky will be most prominent around clusters and even superclusters of clusters. So that's the kind of science I think Roman will just knock out of the park. It'll be just gorgeous.
Now, this is just related to galaxy clusters because, unfortunately, the zone of avoidance, the opaqueness of the Milky Way gets in the way of this, but the Great Attractor. And I know that's an object that people talk about with great mystery, but I personally think it's probably a galaxy cluster. What do you think?
So I think it is part of a supercluster. There are several big galaxies in that, about big galaxy clusters in that general direction on the sky. And so, they like to hang out with other big clusters. That's the way gravity works. And so the Great Attractor or something like it is probably like a supercluster into which we're falling.
We are integrating into a supercluster. Perhaps,
Yay.
But it won't matter because Andromeda is going to hit us long before then.
Yeah.
And what will arrive will be a big elliptical mess called Milkdromeda. And I'm not looking forward to that, even though that's.
I will be really pretty. Yeah.
You know, it would be, especially if you're in a.
Yeah.
Look, when you look into the night sky, with the exception of Andromeda on a very dark sky night, in a very dark location, you can see a smudge.
Right.
But imagine if you could see. And you see the Milky Way, but imagine if you could had a galaxy close enough into your sky that it was the brightness of the moon, and there are such places somewhere in the universe, that you can actually see these things much closer. But we're stuck with the Andromeda galaxy and the Orion Nebula.
I'm glad we're farther out. Because if we were located in the bulge of our own galaxy, our night sky would be full of stars, and it might be sort of hard to see out, right? Because of all the bright stars in your sky. And being 2/3 of the way out, there's directions we can look and there's hardly any bright stars. I mean, for us extragalactic folks, the bright stars of our own galaxy are horrible bright lights, messing up our picture. And so being 2/3 of the way out, we're in a prime position to study the dark universe and see very far out. It's possible if we were really, really close to other stars, we might not have a whole lot of nighttime.
Well, there's another advantage: less chance of being near a supernova that would sterilize your planet.
Or gamma ray burst. That would be bad.
Anything, yeah. I look at. You look at globular clusters, and you're like, all those stars packed in that close. Though that's a sterile environment right there, because of just even if you have a supernova only every 500 million years, that's enough. You're too close.
Right. Evolution takes some time.
Well, Doctor, thank you for joining us today, and I hope that we can at least raise awareness that this telescope, this basically finished telescope, can be saved, and maybe Congress will give it a line item or something like that. But for the Americans out there in the audience, you should write your congressman and say, hey, we got to keep this and keep that one going.
Yeah, the sort of scale to remember is it's basically 92% paid for.
Yep.
And the remaining 5 to 8% is all that's needed to put it into space and make it glorious. And it's sort of like stopping. You have this wonderful house that you invested in and made very nice, and you decided, well, can't afford the driveway, so not only am I not going to keep the house, I'm going to burn it down.
Or the roofing. Yeah, build a house and just leave the roof as plywood.
Just leave it.
Yeah.
Just walk away.
Just walk away.
It's not like you can sell it or repurpose it or something like that. It's got its point, and you don't want to give it away. So use it. Let's play. Do something awesome.
I agree. Thank you, Doctor. And I wish you good luck in your research.
Thank you.